So, I'm just going to give you guys a brief introduction to whatever I have done or whatever on my understanding on this transformer on Heisenberg model. Um, First, I'm going through. This is the reference I include in this talk. The four paper. The first one is attention is all you need. That's where the transformers came from, the base from, and you can in their paper you can find all the network details. And the two papers about restricted Boltzmann machine because this idea using the neural network quantum states to represent the ground state wave functions originally came from the restricted Boltzmann machine. Um, and they just implement this, swap it the RBM out with the transformer. So obviously the PRL paper, the transformer, and quantum Monte Carlo. So our physics system obviously is a 1D Heisenberg model, a spin chain. You have a nearest neighbor interaction and the second nearest neighbor interactions. We're consider the antiferromagnetic magnetic, so J1, J2 is all greater than zero. But to simplify the case, we can set the J2 to zero, which is the second nearest neighbor, and next nearest neighbor, we just set it to zero. So we have a much easier system. I believe this problem is easily you can construct the Hamiltonian matrix, you can diagonalize it, because we know what the spin operator looks like. So it's just a tensor product of two spin one half. You can construct the Hamiltonian and then you can diagonalize it. And then you will have your energy and your wave functions.
So yeah, let me make comments. So if J2 is zero, right, this is just the nearest neighbor Heisenberg model in 1D, right?
Yes,
and
exactly.
I think the people know the ground energy from beta ansatz, so it'd be nice to compare the
Exactly.
variational energy with the exact known result, right?
Exactly. So it's like it's like a test. Obviously, you know what your solution is.
Right.
So you're trying to compare to the same precision, you're 10 to a -4, 10 to a -5, comparing to the exact
That's good.
solutions.
Very good point. Yeah. By the way, let me make a comment that you take this J1, J2 model in 1D. If the J1 is ferromagnetic coupling, J2 is antiferromagnetic, then this model has a very rich phase diagram. And
Yes.
I'm actually very interested in that as well. Yeah.
Okay.
Some new physics there. Yeah.
Yes. So
Okay,
as I said, or as we discussed, this problem is being long studied by they are trying to implement the using neural network, the really easy simple feed-forward network, just like restricted Boltzmann machine, or convolutional neural network, has all been used to tackle this kind of problems. So it's not like new things to trying to implement your quantum state with the neural network. But why the transformer, kind of shine in this way is because essentially your system grow exponentially larger. Every time you have another spin, your Hamiltonian matrix is going to grow at 2n times 2n. For example, if you have two sides, it's going to be 4 by 4. Three sides, it's going to be 8 by 8, dot, 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 dot. It just grows up exponentially. So essentially, you don't have when you go out to, let's say, 100 sites or even 10 sites, you don't have enough memory to store this kind of, Hamiltonian matrix. And you don't have an efficient way to do the exact diagonalization for it. And so that's why, even though in neural network, your matrix or you're given a picture is so big, you don't have essentially a very effective way to learn the feature using convolution or feed-forward. They all suffer from this kind of dimension issue. That's what transformer plays a good role here. But I'm going to a traditional way, and I'm going to the transformer way. So traditional way is you have an RBM machine. RBM machine is nothing but you take your input, add a bias to it, and then feed it into your hidden layer by another bias. So you can write down your energy, variation energy of RBM in this following way. Right. So you can imagine now you just need to play around given a certain spin configuration, 1010, nothing binary, and you just simply varying the AI, B mu, all these kind of variation variable to find the lowest energy. And this lowest energy will give you, this configuration will give you the lowest ground state wave functions.
All right, so I'm
Nothing
just
new. This is
confused.
just RPM.
Could
Yes.
you
Please.
elaborate this a little bit more because I'm not familiar with this restrict Boltzmann machine.
Oh, so restrict Boltzmann machine is based on your statistical physics. Uh, so but it's in the reference, like how did it came up from? It's just from statistical mechanics. I didn't put much details here, but
So
it's
anyway,
in one
so
of my
here
reference.
sigma, the in the end, the variational wave function is
Yes,
sigma is a
yes,
spin configuration. For every spin
yes,
configuration, you need a wave function amplitude, right?
exactly.
And W is
W is the weight. W is the weight of these neurons. It's the variation variable
right.
that
So you're
you
saying that
randomly
okay,
update.
W is like a variational primary, right?
Yes,
And then what is this in this expression for the wave function? A and B and W appears.
it's
A
all the variation variables.
okay, both A and B are also variational parameters.
Yes, they are just biased. So A and B are using with plus. It's like a linear term, and W is like a slope. It's you multiply with your spin configuration.
But the A also
So
couples
that's
with
called
spin configuration, right?
yes, because you take you. It's like when you feed your input here, you're gonna times the A. This is the imp bias. So A times sigma, and then you feed it into your hidden layer.
Okay. Okay. And now this amplitude is always positive, right? So because it's
Yes,
exponential.
you have to use complex numbers when you want to deal with ground state wave function has plus and minus sign, obviously.
Right. But then one thing like if the Hamiltonian for systems of bosons or spins, if there's no frustration, then the ground state wave function is always amplitude is always positive definite,
Yeah.
semi-positive definite. And now in that case, of course, the traditional quantum Monte Carlo methods will work extremely
Mm-hmm.
well, right?
Mm-hmm.
So if they don't have a sign problem, in other words, then just traditional quantum Monte Carlo it will work
Yeah.
very well. There's no need, in other words, for neural network methods,
Mm-hmm.
right?
I agree.
You know
I
what I
agree.
mean?
I agree. I
Okay,
agree. I agree.
that's fine. Here we're just playing with it. Yeah, fine.
But it's like this. If you want to implement in complex, obviously I think there is another form you want to take where you can
Okay,
set your variation up parameters A, B, W, everything in your neural network into complex.
okay,
There
okay.
you
Making
won't suffer
okay,
from the sign
making rest.
problems.
Okay, okay, sounds good. Yeah. All right,
Yeah, but I didn't include it here because I just want to make everything simple,
right.
as simple as possible. So
Wait,
now we
any
go into transformer.
Questions?
So
sorry,
now we go into
question,
transformer.
but
Yeah.
Angus, as far as I know, I think backpropagation doesn't work with complex parameters right now, right? I think the
No,
standard.
yeah, I'm saying these configuration that I put right here, but this is the same paper. All right, this is the same paper as I referenced. They have two model, one for real number, one for complex. If you want to use complex, you have to use the other form
Oh,
for
did
this kind of propagations.
did they implement it?
They implemented.
No, sorry. Yes, they did or did not?
They did. They
They
did.
did. Oh, okay.
They did. Yep.
Okay, I see.
So
Yes.
So they had two separate neural networks, two B muse, one B real and B imaginary.
Yeah, they are
Um,
dealing with one is like the complex term, the other is like the real part term, and they have two part of neural network.
okay.
Uh,
Okay. Okay.
but I just want to make it easier for people to understand here. If you complex is like an issue for you, definitely want to check it out the paper that I implement. But in the transformer, they implement everything. All the variation parameters you see in here is in complex. So
But as
they
far as
don't
I
have this
know,
kind of complex
backpropagation,
issue.
I don't see, as far as I know, backpropagation doesn't work with complex parameters.
I think they do now. They are doing so. If you want to do the back propagation, basically you want to calculate a derivative on a certain complex number, right? For
But you
example,
can't.
partial
It's like
energy.
yeah, it's
I think you want to check it out right now. I think they implemented already, even in PyTorch or in JAX. They have an automatic differentiation that can do the gradient. They can do the backpropagation on the gradient. On the complex number.
Okay. Did you share the
They
link?
follow the yeah. But all right. Anyways, I'm going to the transformer. So
Okay.
transformer, you have a chain of spins. It's the same problem. You have a single chain, up and down, up, down, up, down, up, down. What you do is you're going to feed the same you want to cut them into clusters, for example, up, down, down, up, down, 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 this kind of certain configurations. And why people are interested in implement this problem in the transformer way is because this is the same behavior as the sentences or language learning models, right? You have what configuration will give you the lowest energy. It has to be the lowest in the cluster and also the lowest in the global relative position, which means it has to be the lowest ground state, which is you see the total SZ is equal to 0. And also you have to, switch the cluster positions. This is just nothing but like a sentence. You given a certain, it has to be the correct combination of letter to form into a words, and then the correct position of each words into a sentences. So this is like the mapping between the language model to the spins.
Yeah, no, this is very good. Yeah,
Questions?
very good point. Yeah,
Questions?
yeah,
Questions?
I
All right.
like it.
Then I'll go through more details.
Yeah, this
All right.
analogy is very inspirational. Very good.
So what information or what is the most essential things in your transformer is QKV values, queries, keys, and values. These are the three matrices. Um, I sort of don't really understand why you need the QKV values right now, but I think in the attention in the Google paper they just saying like this is the way how our brain learns the languages. But this mapping I didn't get it, but whatever. So what we actually do here is, we have a spin, right? We cut them into clusters. You map it into the binary. Yes, please. Yeah, of course, of course. Keep going, keep going, keep going, keep going. Oh no, 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 no. I'm saying the Google. How did they come up? How did they come up this kind of analogy? How our brain learns the languages? This part I don't get it. I don't know where it came from. Yeah, sure. You feel free. Feel free. Just coming up. Yeah. Mm-hmm. 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 And then you. Mm-hmm. 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 Ooh. No, I love it. I love this kind of, easier or grammar understanding way of implementing this kind of things. I love it. All right,
Hey,
thank
but
you.
these are
Appreciate it.
just linear transformations, right? These are
Yeah,
linear
yeah.
transformations.
It's just it's just
Linear
nothing but
transformations.
linear transformations. Yeah.
Yeah.
All right. Let me keep going through
And then now,
what I'm going to say.
they're grouped in three, and every three spins grouped into one.
Oh no,
One.
it's fine. It's you can decide it. I just give an example. It can be whatever
Okay.
cluster size you want it to be. It can be 6 spins. It can be 8 spin. Whatever. It's just I did it because I did it in some system that is 3 spins. So I just found it
Okay.
more straightforward. Give it example three
Okay.
spins.
Fine. Yeah.
So yeah, by just like what I put it here. You have queries, keys, and values. Each are going to be calculated nothing by a matrix product QKV matrices. These are all rectangular matrices right here, 3 by 3, because I have my embedding or my input vectors
Uh-huh.
is just a 3 by 1 vector, right? So it's a 3 by 3 matrices. And QKV are the variation parameters, just like, in the RBM machine, the A, B, the input and bias weight. These are the variation parameters that you're going to, keep variating, and that will give you the lowest ground state energy. All right. So what makes transformer different is the attention layer. So attention layer, they have two choices. The first one is a
So
scale dot
before we
product
go,
attention.
Angus, can I ask you
Oh, yes,
a
please.
level, sort of a high level question? Okay. So is a general idea that go back to the previous slides that you're going to actually the previous slide one more. Yeah, is basically the variational wave function is always of this form. It
Yeah.
has variational parameters a, b, and m, and
Mm-hmm.
then the task is to optimize b and m,
Yes.
a, b, and w. Sorry, a, b, and w, and
Yes.
you're using the transformer to optimize it.
Yes.
That's the basic high level picture.
Exactly.
Okay.
And then the ultimate high level picture is you want to swap out this W into the A's.
Swap the W into the A's.
Right?
Meaning,
Your W is nothing but your neural network, right? It's W is just this kind of layer, the hidden layer that give you a certain weight. You multiply it on your spin configuration, right?
right?
You just want to swap out this W with the transformer. So the transformer here, the entire things you can imagine that's a W.
Is W. Okay. Okay.
It's just a more powerful way to
Okay.
implement your weight,
Okay. Okay.
right? So that's really I'm going to say in the end or in this slide. I'm
Okay.
going to go through the scale dot attention. This is the most easy way of attention, and it has this form. So it's alpha. Alpha is the attention weight, and attention weight is exponential minus c. This is like a Boltzmann. This is like a Boltzmann weight, or in machine learning language we call it softmax. This is the part that Cash mentioned. You have the dot product, you have the queries and keys dot product, and you're gonna scale it, and then you're gonna calculate what's a softmax or what is the Boltzmann weight of it. Concatenate with your values. This will give you the attention layer. In my physics picture, what it actually did is instead of looking just in your cluster, you have this kind of attention, which cares about, KJ, right? KJ is the other, the people that were the cluster that near you. So you're gonna have the information from them, you concatenate it with their values. So it's again it's their information. You're gonna take it into account and then consider yourself, your local information. So it's like a local information plus the global information, right? That part will solve this kind of relative position problem. Uh, yeah, but ultimately you just want to replace your W with the AI, and then use the same form of your variation wave functions. And that's why we pick the log cosh in the paper. That's why they pick the log cosh, is because this kind of form just gives you a hint of what your activation function should be, right? So now you just need, just let the machine sort of perform the gradient descent on all of your variation parameter to find what the lowest ground state wave function is. But this wave function doesn't include any symmetries. So you have to encode that. The easiest, or the most easier way, or easier symmetry that this spin chain should preserve is a translation symmetry. What I mean by translation symmetry is if you have a down up, up down, if you switch them, they should give you the same energy, right? Because it's the same configuration, but just shifting the position. But that should still give you the same energy. So you're just going to have this kind of transformation matrix that can give you the information of how the cluster can interchange between them. But this is the same argument as they have in their paper, which is called the position encoding. But this is sort of you don't need the position encoding to get the right energy. But I'm just telling you, this is kind of like a thing that exists. If you want to preserve the symmetry, or if you want to add a symmetry, you just need this kind of operator or this kind of matrices that can implement it. All right. Now we go into loss functions. So the loss functions obviously is our energy. ML is all about data and loss functions. So data obviously is our spin configuration, which is, I think, the most difficult way to generate our data in physics system, because for this kind of system, if L goes to 100, there is no way you can store all the possible spin configuration, right? Like imagine how big the matrix is going to be. So there's no way you can, actually storage it in somewhere and then train it with the, what the computer science people do, playing with their data. This is not possible in physics. So you have to use the quantum Monte Carlo. And when you have the quantum Monte Carlo, things just get a little bit difficult, because you cannot perform the gradient descent on the energy directly with the normal gradient descent. It has to be a certain way of performing it. But I won't go through that much details, but I put a reference here. This books, chapter 6.3 is what I follow to perform the quantum Monte Carlo part. And this is actually the same people who did this translation variation wave functions. So I'm pretty sure they follow this kind of approach to perform the quantum Monte Carlo, also how to update your variables, perform the gradient descent on your energy. And the last is so they already did this 1D chain on 100 sites and compared to the DMRG results. That's pretty much like a benchmark already. So what kind of problem can you still do? As Liang say, you probably can do, J1, J2, different phase diagrams, something like that. But what I think it's also another way to doing things is What about you switching to the eigenstate instead of spin configuration, right? You can switch it to eigenstate. Imagine you have a four-side system. You have two clusters. Each cluster have two spins. Essentially, what you're having is a singlet or triplets combination, right? So this is the form of your ground state wave functions. You can also learn, you can also learn the ground state wave function of this kind of system. I think that's definitely possible things to do. Or even higher dimension, instead of 2D 1D chain, you have a 2D lattices. Or you cut a chain, you already cut the chain into clusters, three clusters, 3 spins, 4 spins, whatever. You can study the couple cluster theory. There's a reference of this kind of problems. I put it here. If you take a look at the form, you will find it is exactly the same behavior as your cluster, right? This cluster interact with this clusters and it's going to interact with the second nearest neighbor. We already have this kind of system, so why not, right? I think that's pretty much I wanted to say it right here. I just want to give you a very, intro level of what the transformer did. But I'm being really concise of something.
Yeah,
so
no, this is very good.
let me know if you want me to put out more details or technical details, because to be honest, this problem or this kind of problem to me, the hardest part is quantum Monte Carlo. Neural network is easy.
Yeah.
Right. Neural network is never the problems, but the data is the most difficult part. Right. You don't have this 100 sites spin configuration. That's the most important part.
So yeah, this is fantastic. Thank you, Angus. Yeah, the talk is very clear. That's exactly the kind of high level we need, and then we can all ask more detailed questions, right? So I have a question. So if you think about this, people sometimes ask me this question, and I don't know how what's a good answer. Since we're doing a variational calculation, right? And in fact, you have an ansatz, which is a restricted form of the wave function, right? Why this cannot be done 20 years ago? Now, there's no training data, right? We're just doing the variational Monte Carlo. So why cannot be done 20 years ago?
Because you suffer from the
that make it possible now.
It's very computational inefficient. If you implement in the RBM machine, I think but that's for 2D system. I'm not sure, but for 1D system, I think above 20 sites.
Yeah,
it's already very, very computational costly.
You mean do
just
it directly?
Doing directly is very, difficult.
So okay, so then why the neural network makes this optimization problem so much more efficient?
Oh, because for this transformer, why it can grows up to 100 sites is because you can always cut your spins into clusters. So let's imagine you have 100 sites. You can cut them into 50 clusters. Each cluster just only have 2 sites.
Yeah.
Your QKV value is just 2x2 matrices. And you just need the 50 heads of multi-head attention, to looking at those. So your neural network doesn't grows up exponentially. And that's the most important part, why you can scales up.
Wait, but let me ask that. Each block, let's call the 3 spins a block, right?
Yeah.
Each block has its own, QVK, variational parameters, right? And the different blocks can have different variational parameters.
It depends on your head. So QKV came from your heads. Like, how many heads you're going to have your attention?
Heads meaning what?
So what's that? Sorry?
What does head mean here?
Head means how many, if you have 3 heads, you're just going to have 3 sets of QKV values. Each head has its own QKV. So let me go through this slide. So this is the different. What do I mean by head? This is the head. This is just a single head. The single head is what I did here is a Q dot K times V. This is for single head. Multi-head means you have multiple this kind of scaled up attention. Each head is going to only have Qs and Ks and Vs.
Yeah, but
So
in
you
this
see
particular
why?
problem, in this particular problem,
Yes,
can I say that when I choose to group three spins into a block, into a unit,
yes, yes,
then each unit has one head,
yes,
right?
yes.
So okay, so the number of heads basically grows linearly with system size, right? In
Um,
if you have if you have a
I think
99,
in their argument, yeah, it's somewhat gross, but in their argument, they are saying like you don't need that much variable to describe your system, because essentially you definitely do have enough variables in your system to describe a gross wave functions. It's not like a one-to-one correspond.
so are you saying that this Q, K, and V are the same for different units?
Yeah, yeah.
Is that what I'm saying?
For head, for in head, in single head. If you just had head, they are going to use the same QKV. The QKV is just all 3 by 3
Right, and it's the same for
for all, no matter
all the
how much
units,
your
for all
system
the
size is
units.
going to.
Okay,
Yes, yes,
right.
for all the
Oh,
units.
oh, I think I see what you're saying. You're saying each head is one set of QKV.
Yes,
Can I think
yes.
that way?
So yes, exactly. That's what I meant.
Okay, interesting. Can I look at then the neural structure again? Neural the transformer structure. And
Yes.
okay, there's that. Could you explain the figure here?
Okay. So
We
you
have
take so imagine in the RBM machine, what
yeah,
we did is we have a spin configuration, right? It's an input with plus a bias,
yeah.
and then we fit it into a linear neural network, or like we call it hidden layer. So
But
that's
each
already give you a
linear,
bias.
each unit will call you linear. It only acts
Yeah.
on three spins in the entire chain.
Yes. Yes.
These
Yes.
different linears are actually using the same what do you call the KPVs.
QKVs. Yes. QKVs. Yes.
Okay, yeah, each linear,
Yes.
okay, each processing unit that they call linear actually
Mm-hmm.
using the same set of variational parameters.
Mm-hmm.
I see, and then multi-head, but then the number of the linear processing units grows with system size, right? Because each linear processing unit only takes three spins. If you have a system with 300
Mm-hmm.
spins, then you will
Mm-hmm.
have 100 such linear units, right? You have 300, 100 linear processors, let's call it that way, right? I mean, I understand they all use the same variational parameter, that's fine. But then when you
Yes.
talk about this multi-head attention, that has to handle 100 inputs.
Yes. You have you probably need, a certain amount of heads. Yes, I agree.
Yeah.
Uh, but
And
I'm
then,
I'm I'm maybe I'm saying like in their paper, they
but
never
what I'm
say.
really trying to say, at the end of the day is, if you think about your variational parameter, right? Are
Mm-hmm.
you essentially assuming that there's every block of three spins, they have same kind of variational parameter? So you're essentially saying that in the end, the number of variational parameters are actually still very small.
Mm-hmm.
Is
Mm-hmm.
that is that is that the same as saying that?
Mm-hmm. That's why I started trying to argue, or trying to say why you can make a difference, or that's my understanding, because uh in what I feel like in real words, what they do it, your QKV value never scales up with a system size.
Okay, the
But
QKD
your
never
head,
scales
but
with
your
size.
yeah, yeah, because that's what I'm saying. Like you can always chop it into a smaller cluster, but yeah, you need a you need a certain amount of heads, and that's what probably is going to scales up as your system size, but it's still not scales
Yeah,
up
is it like to say
exponentially.
that that I'm actually using a variational wave function where the number of variational parameters does not scale with system size?
Yes,
Think that way.
I think so. Yes.
Then why the? But again, one can if you go to the
Mm-hmm.
form of the variational wave function, right? Then
Mm-hmm.
even without using the neural network, right? I can if you go to the restrict Boltzmann machine wave function,
Mm-hmm.
I can just design a variational wave function which, for example, only
Mm-hmm.
depends on the correlation between two adjacent spins or something, right?
Mm-hmm.
I can suddenly
Mm-hmm.
design a variational wave function which is translation invariant, right?
Mm-hmm.
And then in that case, can I just directly optimize the whole thing?
Yes, I think so. That's totally doable. As I said, it's the same. Like it's computationally expensive, I think. And then you
Okay.
want to compare to DMRG, which is basically the
Okay.
exact
Yeah.
solutions in this
Yeah.
kind of computational method. I don't think they can give you the same precisions right there.
Yeah. That
That's a
seems very
problem.
interesting. Yeah.
Yeah.
Uh, Right. Right. Sure. Yeah. 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 Right. Right. No, I'm trying to still kind of get it. My gut feeling, right, is that there must be that with neural networks, you trade some expensive numerical matrix manipulations with some cheap ones. That's my gut feeling, right?
Mm-hmm. Mm-hmm.
But I don't exactly know what are the difficult things that are being given up, and what are the cheap proxy for that is not being used. So that's kind of thing I'm curious about. Yeah, but this is a very good discussion to start with. Yeah, angles. Yeah, this is very good.
Mm-hmm. Yeah, but this is or like all I'm saying, like
Yeah,
this is a very introductory level.
yeah,
If you're really interested in these kind of problems,
yeah,
you definitely
yeah.
should want to checking out like the reference I put it here, because that's what reference I go through. So
Sounds
like
very
I'm
good.
saying, like the rest of people, if you're interested in this work, and there's a I just found there's a notebook or a paper that have RBM implement in the Python. I think it's in PyTorch, and they publish everything. The code is open source. Uh, you can start from there if you're really interested in this kind of machine learning problems. That's a good starting point.
Sounds good.
Yeah. The archive, the 18031. Yeah. That one they do a lot of problem in that notebook, so it's a very interesting one. If you,
Okay.
Mhm. Yes, 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 yes. Mm-hmm, 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 mm-hmm.
Yeah, yeah. So catch, yeah, yeah. No, I think they're two different issues, right? So I think yeah. So one first, for this problem we're dealing with, right? All the problem we have been discussing. I mean, I don't know why should we call it learning or should we just call it optimization, right?
Uh,
You don't have
okay.
any training data.
You should call it optimization,
Yeah,
and
exactly.
optimization is the same as unsupervised learning in machine learning language,
Okay,
which actually counter what Kosh said. You don't have the data. You cannot do the same implementation. You cannot let the machine learn a 100 site configuration and generate a 1,000 site
okay.
spin
So that's
configuration.
exactly
That's
the
not
next
possible.
point. That's exactly the next point I have always wanted to wonder about that. Okay, so
Nope.
so it's okay. So okay. Let's talk about this here. Okay,
Mm-hmm.
so I think what you want, okay, is something I always wondered, and I think people are
Mm-hmm.
already starting to work on this. It's
Mm-hmm.
called transfer learning. Okay, you want to
Mm-hmm.
basically do some optimization for a small system,
Mm-hmm.
and then you want to use what you learned and
Mm-hmm.
apply it in some meaningful way for
Mm-hmm.
larger system. Okay,
Mm-hmm.
anyway, this is very natural because for us in condensed matter physics, right, Hamiltonian is the same. We want to understand the ground state Hamiltonian in a certain limit,
Mm-hmm.
right?
Mm-hmm.
For small system size, we have no problem doing numerics. We can do ED, okay?
Yes.
But the real issue is, about large system size.
Yes.
So the question is, what do you learn by doing? Can you learn something, right, from small system size
Mm-hmm.
and transfer it to large system size?
Mm-hmm.
This is called
Mm-hmm.
transfer learning. Okay.
Yes.
And people are just starting to play with it. In fact, aiming Fermi-net, people are just starting to do this. I found a yeah.
So I was in a different field, but I see something extremely similar. I'm
Uh-huh.
just going through it. So what I see is there's a thing called deep edge. What you learn is the DFT Hamiltonian. So you can learn for twisted bilayer graphene is essentially a very large system, right?
Yeah.
You just learn given it a certain, very tiny graphene configuration, and you
Yeah.
can predict the Hamiltonian for twisted
Well,
bilayer
yeah.
graphenes.
That's another problem very interesting, and that I think is to some extent a much easier problem.
Yeah, that's an easier problem. The people already implemented it. It's not a
people
big
call it
deal.
downfolding, right? Downfolding
Yeah.
problem. You want to
Mhm.
basically learn the effective Hamiltonian that governs the low energy degree of freedom. That's a much easier problem.
Mhm.
And I'm more interested in, suppose you're given the Hamiltonian. I want to know what the ground state is in a certain limit. Then transfer learning is extremely useful if we can if we know how to do it. Yeah. So
So in that case, you might want to design your loss functions in a
yeah.
very elegant way. I'm not sure if energy is still the same, can still be the same loss function in that case, in the transfer learning
Yeah.
case, because
Yeah.
I'm
I
not so
mean,
sure.
I think there are various simple things one can do in that direction. Yeah. Simple things.
Okay.
So but yeah, very good. This is fantastic. Yeah, thank you, Angus. Any other questions? Yeah.
Angus, yeah, I have a few questions.
Come on. Yes.
Yeah, so going back to this discussion around multi-head attention, you mentioned that the number of heads basically determines the number of like QKV tuples you need, right?
Mhm.
So my question is, how exactly are you determining the number of heads you need? Is this like empirical completely,
It's a
or
hyperparameter. So
okay.
what I like to call is an art. There is some rules, which means your head should always be a certain, a certain amount that should be matching as your data points. But there is no, it can be one, it can be whatever amount. It's like an art or hyperparameter that you want to test it on.
Okay,
Right?
so can you give like a order of magnitude estimate? Like if I have like
Oh.
100 spins or like here 33, groups of 3 spins, right? How many heads would you like typically need?
If I'm going 33, right? So
Yeah.
I think it's, let me think. I think in the paper, I'll probably go with, I think either 3 or 11 is enough.
3 or
It has
11?
to, so yeah, it has to be a factor of whatever your input cluster is. So you're given 33, right? So the factor is 3 times 11. So I think it can be 3 or it can be 11. I think there is a certain designing logic behind it. That's what I remember, or what I recall is correct.
Okay. Okay.
If you really like, this is I need to check with back into paper, but I'm pretty sure they have discussed all the all the consideration, or how good or how efficient you have certain amount of heads
Yeah.
will be. So they have discussed that already, but you just have to check it out.
Okay, I see. Second question, maybe you already explained this earlier and I missed it, but so
That's fine.
here, like I understand, with the transformers, you're saying basically why it's computationally more efficient. It's just that you're simply breaking up, if you have like 99 spins, you're breaking up into 33 groups of 3, and then you can work with much smaller matrices, right? So then although like because your physical problem is still like a 1D Heisenberg chain, right? So
Yes.
these, like if I just imagine me cutting down this like 1D chain into these groups of 3, there are still interactions between the spins from neighboring groups, right? So at what
Exactly.
point in this transformer architecture are you taking that into account? Is this
Yeah.
like when you are
The
in the multi-head attention, or?
No, it's in your attention. It's in your it's so basically interaction. What you interaction, you can think of it as a cluster interaction. What you want to do is basically just switching the position, right? You can that's one possible things you can do. Just switching the positions of them, of the entire cluster, and that's already implemented in your in here. I believe.
Okay, so are you like switching through all possible cluster configurations or just switching through some of them to test how like the energy changes?
That's like a part of quantum Monte Carlo. You just switch one and then you test it. You test how the variation will change. If it's acceptable, you pick it, and then you just do it again.
No, I
If that
thought
makes
the
sense.
quantum Monte Carlo was how you were generating the training data. Not
Both
I'm
for
asking
both.
like in the transformer architecture
Oh,
itself, where are you taking this
oh,
into account?
my bad. I think there is one thing. I think it's here. I think it's the translation symmetry. What we actually do is we just have a matrices that can record, what's the coefficient should be changing when you interswitch the 1 and 2 cluster, 2 and 3 clusters for 1 and 3 clusters. And that's what goes into the neural network. I think it goes into here. You just multiply by an Rij here. That will give you this kind of position encoding or this kind of relative position
Mm.
or how the cluster should be interchanged. I think it's going here. It's in here. You need a matrix called Rij, and this is also another variation of parameters, and that should be symmetry because one switch to 2 and 2 switch to 1, they should be the same. One should switch to 1 is nothing, and the diagonal component should be 0, and all the rest should be symmetry.
Okay.
Right, if that makes sense. But I didn't know it will be that question coming out, so I didn't prepare it. But that's how we do it. How I put that information when I deal with translation symmetry.
Mm-hmm.
Mm-hmm. Or how the cluster interaction came from.
I see.
Okay. I have a couple of questions. So this works. So this works for 1D. Does it work for 2D?
Definitely, because what the architecture they base on is called vision. It's called vision transformer, and it's already designed for 2D. Imagine you just having your linear here. It's a linear, but you can switch it to convolution neural network instead of taking the vector. You just have a convolution neural network there to scan through the pictures, right? No
Okay.
big deal. I think it's
I
totally
guess to be
possible.
more precise, have they done it on a 2D Heisenberg model?
Nope. Nope, they didn't done it. I don't think they done it, but
Okay.
you can already do the same problem on RBM machine, right? So if you have the same analogy, you can definitely do it on 2D material, the 2D system, the 2D Heisenberg model, easiest way.
Let's phrase it another way. Has any group has any group tried this LLM model on any 2D models?
I want to say there are people doing it. I'm not sure how their progress have been done, but there are some groups trying to do it, as far as I know. Right.
Okay, so trying means you know of friends who are working on it, or like they actually have published results.
No, they don't have published result, but like they are working on it.
Okay.
Yeah, so I think the Fermi net, this kind of a thing has been applied to 2D and three-dimensional materials, right? So that or transformer type of neural network. I guess what Angus is saying that nobody has published results on higher dimensions.
Yes,
Okay, fine.
But what's this
I'm
paper again? Sorry, could you sorry,
that's fine. I can go through. Yes, this is just called translation variation wave functions for frustrated constant spin system. This one, the third one.
Okay.
Yeah.
Okay, can I ask a question?
Yeah,
please go ahead.
Yeah, so are there any like universality results, like saying that with, let's say, like a polynomial number of parameters or something, you can capture like all, let's say, all area loss states or anything like that? Like, are there any such results?
Yeah, I think people study this problem. Like, basically, what David is asking is the expressibility of random Boltzmann machine wave functions, right?
I think there is
Exactly,
one.
yeah.
I think there is. But I think it's I think there's a problem with restrict Boltzmann machine, but I can't forget the argument for that. I can't remember the argument for that. I think but I think people already studied. I don't think it's that expressive enough if you have an exponential grow up system, because in the form of the variation wave functions, your W matrix has to grow as your system like grows exponentially, right? So I don't think RBM is that expressive now if you have
No,
extremely
no, I
large
think the
system.
question is that if you allow all the
Mhm.
parameters, right? If you allow
Mhm.
sufficient number of parameters, maybe it's universal enough. Maybe it's very can express a
Yes,
lot. But in practice,
yeah, I think that in that way it's possible.
yeah,
It's probably not.
yeah, I think that there are these studies of this kind of problems. Yeah,
Mhm.
the literature. I remember long time back seeing papers. Yeah, very good. Other questions?
Question. And how does
Mhm.
the neural network represent long-range entanglement? So when you compare to DMRG, for example, they are good for, or matrix product states, they are good
Right.
for short entangled states, but long-range entangled metals they cannot represent. So, but I think I've seen some papers on how that neural network can do that. So how do you do that? Do you need multiple layers of those attention layers, or
Mhm.
what are the limitations?
This is this is the I would say, okay, I would say this kind of question can be done by the same R matrices by representing the correlation between this, the first cluster to, the 10 cluster. What are the interaction between them, right? That's what the R matrix is going to be done.
Sorry,
I
which
believe
matrix is
that's
this?
where it
R
came from.
matrix? Sorry, what? Sorry,
Yes,
which?
R matrices is like a position encoding matrices.
Oh,
I didn't put it here because I don't want it to make it so difficult. Position encoding is like an optional things for transformer. You can put it there to giving you a position encoded that can actually learns the sentences better, which means you can learn the whole structure better. But that's like optional things. It's not necessary. It depends on your problem. If you want to deal with the long range, you definitely want to include that position encoding.
Okay.
That will have the information of whatever side you want and whatever words in your sentences. Right.
Okay, I see. So I suppose it will put a bound on the complexity, or you do an architecture that can capture.
It's the architecture. It's the architecture, I believe. It's the architecture.
I see.
But you have to design it. If you this is just very specific problems. But you probably just want to put position encoding is what they are solving this kind of problem in the transformer. In the paper they did it as well. They did put the position encoding.
Okay, I see.
Mm-hmm.
Thank you.
All right, you're welcome.
Right.
Oh, by the way, they have the code published, not like published. They have their own package for this paper. I think it's called Netkit, Netket. If you search on GitHub, you can find their source code.
NATK.
Netket. Netket. Netket.
Sounds
Yes.
good.
And
This is the yes for this. This GitHub is published by them by this paper by this group of people.
Cool.
Okay. And in this Netkit, I also find how they do this long range entanglement structure with the.
They have a lot of system doing over there. So you can check them out.
Okay, thank you.
There you go.
Yeah. Okay. Thank you again, Angus. So, quick thing, like, Cash, did you get a chance? Any, we needed this high level presentations, but also, one of the goal is to get students to actually implement some of these. So, Cash, did you get a chance to play with Fermina a little bit more? Any quick update? You can maybe some demo, some code demonstration, right? A very simple system, maybe 2 electrons, for example, right? Can you, run the Fermi net and really give us energy for 2 electrons? Right? It's this kind of thing. I think if you can do a demonstration, yeah. That's not. But I'm saying, but do you have that capability? Are you able to, for example, run the Fermi net for 2 electrons? Yeah. And that would be useful, if you can demonstrate, if you can just in some of our meetings, if you can just demonstrate that, right, just to show how you run the code and get successful, and that's a great it'll boost the moral. I think it will boost the moral. Yeah. Yeah. Okay. Anyway, no, not it's not we need to do today. Yeah, but I think that's the goal, right? That's a goal. Yeah. To ultimately we have our own handle, right? Handle on the on these things, not just presentations, but actually we can implement it and use it to do something we are interested in, right? Does it make sense, Catch? Yeah. Right. Yes. Yes. Yeah, sure, sure. Just take your time. There's no hurry. Yeah. Sounds good. Excellent. Yeah, but keep us updated. Yeah. Okay, and then next week I think Tony actually, and I remember Tony promised that he could do continue to talk about FermiNet next week. I think. Then we just need to talk about the week after next. Let's see. The week after next will be yeah, the week after next. I think I might be. Are we in San Sebastian that week? Uh, I think I'll be traveling. Huh? Sorry. Yeah, San Sebastian. Right, right, right. So maybe then the week after that will be July 22nd. Yeah. So we need to
I
discuss
can do
that week.
something that week.
Okay, sounds good. Yeah, maybe Aiden can do something that week. Yeah, that'll be useful. Okay, yeah. So it'll be Tony, assuming that he's still available next week, and then 2 weeks after that it'll be Aiden. Sounds good.
Cool.
Okay. Yeah. Any other suggestions, feedbacks? Okay. Yeah. Then sounds good. Yeah. Thank you all. Yeah. Great. Yeah. Bye.
Thank you.